is Barry Rowlingson from the University of Lancaster, or Lancaster University. He's going to speak about some work he's been doing with tropical medicine.
Right, thank you, Laura. Yeah, I'm a research associate in the fairly new School of Health and Medicine. And I work in this unit called GCAS, which stands for Combining Health Information, Computation and Statistics. So we're essentially partly statistical experts, partly computational experts. Actually, that's just me. Everyone else is a statistical expert. And what I want to do today is just run through a couple of applications that we've done. Page down. A couple of projects where we've implemented some statistical methodologies, some novel statistical methodology into a real-world tropical medicine application. Now, I like coming up with acronyms for things, and they seem to start with A. The two things I want to talk about are called RLAT and Amensis. Now, RLAT is a desktop mapping application, which is built on top of Quantum GIS. And Amensis is a wonderfully buzzwordy thing, a web analytics dashboard. These are big buzzwords these days, analytics and dashboards. Everyone seems to want to do enterprise analytic dashboards. Sorry, did I miss a buzzword?
Cloud.
Cloud-based. It's web rather than cloud.
Surely it's snow-based.
Yeah. Okay. So, RLAT. There's a map of Africa, and along in that region of Africa, it's heavily affected by lymphatic filariasis. This is also known as river blindness, and it causes blindness, which is clearly a major debilitative condition for people living in this region. But it's treatable. You can dose people with Mectizan, and the company, I think it's Merck, have donated massive amounts of Mectizan to treat lymphatic filariasis in this region. And you can treat people with that, and they don't get the lymphatic filariasis. Now, the problem with that is that Mectizan kills an awful lot of things in your system. It's designed to kill these nematode worms that kind of crawl around in your lymphatic system. And these are not Mectizan, these are not lymphatic filariasis worms. These are lower worms, which are a different breed of worm altogether. And they live quite happily in your system. They don't cause blindness. But if the Mectizan kills them all off suddenly, it can produce what's called a sudden adverse neurological effect, which is basically massive hemorrhaging and death in many cases. So quite rightly, the people who live in this region are suspicious of the Mectizan treatment. So what the World Health Authority needs to do is to find out where are these lower worms prevalent, so that when they go and treat with Mectizan, they can have more doctors, special treatments to cope with the adverse effects, so they can do this kind of treatment without, but keep the villagers happy that where they're treated. Okay, so we need to go and get some data on where these lower worms are. Two ways of doing that. The first way they tried was to go around in a Land Rover around these remote regions, take blood surveys from a number of people in each village, take a sample of people in each village, and take a blood survey, take it back to a big city hospital with a lab, do a blood smear test, look for these parasites, count them, work out how many people had the parasite in the system. But that's expensive, it's slow, takes a lot of resources. It is, however, accurate. You've got a fairly good measure of whether someone has the parasites if they've got them in their blood. The alternative way, illustrated by the clipboard, is by a survey. They basically went to a number of people in the village with a picture of that worm, or something like it, and said, have you ever had one of these crawl across your eye? Have you ever had these other symptoms? And they used that as a rapid survey tool for getting a less accurate measure than blood surveys, but much cheaper, that they could roll out all over the place. You could probably even do it by not even going to the village if they've got some communications. You could probably fax them a picture, fax them the survey and say, can you just do this to 100 people in your village and send us back the results? It's much cheaper. This is the rapid, lower lower analysis tool, wrap lower. Now, that gives us point estimates in a bunch of villages. We want to know what's the prevalence of places that we haven't been to. And we can add in all sorts of other data. We know these worms don't survive in high altitudes or extremely hot places. So we can feed in satellite data, remote sense data, weather information. We can bung all that into the mix and produce a statistical model that will tell us where these worms are. So, bit of statistics. We're going to construct a bivariate binomial spatially correlated model with covariates that takes our data and our satellite information and gives us predictions of where these worms are. I'll go through these terms because some of you may have seen one or more of these terms. This is how we tend to do stats. We put together a whole bunch of horrible looking words into something new that no one's bothered analysing before. It's bivariate because we've got two sets of data. We've got a measurement of the prevalence from the surveys and a measure of the prevalence from the blood samples. And the behaviour of those measurements, those samples, is different. So we've got to treat them differently. We can't just bung those two sets of numbers together and treat them as the same thing. So that's bivariate. Binomial means what we've got is we've tested a number of people from the village and a certain number had the parasite. That's binomial data. It's a binomial response. Spatially correlated means that we expect that if it's high in one location, it will be high next door to it. It's spatially smooth. So spatially correlated data. And our model has covariates, which are our satellite data, which are other information that we can throw into the mix to try and make predictions. And this is quite a complicated thing, which is why you won't find a drop-down option in SPSS or any other stats package. Click, bivariate binomial spatial correlated model with covariates. You won't find it. In fact, modelling that kind of thing didn't exist until, what was this, 2000 and, I can't remember when I wrote this paper. But the technique for modelling this kind of thing, developed by my two statistically competent co-authors and myself, came out in the Journal of the American Statistical Association 4 or 5 years ago. And so anyone can go to the library and read all 42 pages of it and work out how to predict lower incidence across Africa. Okay, so everybody click 1 if you think you could do that. No, it's not like that. If you think you could do that now by reading the paper. Okay. In the old days, before the internet, that was all you got from statisticians. You got a paper, you got some equations. If you were lucky, you could write to them and say, could I have your Fortran code, please? And they'd send it to you on a floppy disk. It might run on your machine.
Punch cards?
Or punch cards. You're not that old, sir. I don't believe you. But nowadays, we've got the internet. We can implement this. And thanks to sort of the open source ideas, concepts, we can distribute it. And we can get it to people. Now what we've done is we've implemented this, or I've implemented it, in R, which is an open source statistics system, which is essentially a programming language for doing statistics, a whole bunch of libraries, packages for doing just thousands and thousands of statistical analyses, and a graphics engine that can produce publication quality output. It's completely free, it's completely open source, it is the leading statistics package in every UK university and pretty much every university around the world. We all use it. It's got a massive community, it's very well developed, it's regular outputs, and you can make it do just about any stats you want. Now, okay, click 1 if you think you can type that in and do the analysis. Okay, it's getting easier. It's getting easier. And I can make it even more easy by wrapping all these lines of code into one function. And our end users could just read the data into R, run one line of code, and then map the output. Because the way you can, the power of a programming language is that you can wrap these concepts into smaller concepts and make things easier and simpler, and get everything down to one line. And the crucial line here is just the one at the bottom. X equals exceedance probability, y hat SD 20, image of EX. What that computes is the probability that the prevalence of these lower worms at the grid of locations is above 20%. Okay. So our model says things like, we're 95% sure there's more than 20% people infected. Or it says, we're 95% sure that there's less than 20%. Or we could say, we're 50-50 whether there's more than 20 infected. It gives us this probability that it exceeds this 20%. Now this 20% is the magic number that the World Health Organization say that's where we have to take special measures when we treat nectar. So if the area's more than 1 in 5, we better take care. If 1 in 30 people have been infected with lower, that's okay, we'll just go and do it. Now these two lines of R at the bottom there produce a map like that. It's a rubbish map, it doesn't have a scale, doesn't have a north arrow, doesn't have any context to it. It's still a map. And you can get maps like that out of R, plots like that. The white region here is the high area, so that is where we are sure that the prevalence is over 20%. The red region is where we're sure that the prevalence is below 20%. And the yellow areas and the shades in between are areas where we're not sure of the probability. Well, we're sure of the probability, but we're not sure if it's above or below that 20%. That's a kind of grey area. Now we could map that in different colours. We could do that in grey. We could put scales, and you can do maps and things in R. You can actually put base map data on and load in Google Maps, and I work out how to load the survey data at some point. But it's still a bit tricky for end users, especially if we're dealing with developing countries who perhaps don't have skills in programming and so forth. And we want to give them a tool that they can use on their laptops in the field, where they can go out and do these surveys, type their new data in, and get new maps straight away. So I had a quick review of open source geospatial technologies, and realised that I needed to make a desktop application that was self-contained for a user on a single machine. I chose QuantumJS partly because I programmed in Python. If I was a Java programmer, I would have gone, let's use OpenJump, or is GVSig Java? I would have used one of the other tools. And I've got a choice. I'm not constrained to anything. Python is a programming language that it fits my brain. You find programming languages fit your brain. So eventually you'll find one that fits your brain. And QuantumJS can be extended by programming in Python. Python can call R, and then R can create mapping kind of outputs that can be read back into QuantumJS. So the operator of QuantumJS can sit in there. They can be doing complex analysis, statistical analysis in R without knowing. They don't need to know. I'll step through how it goes. There's a QuantumJS screenshot. This is quite an old version. It's actually 1.0. And you can load up a simple base map. Here we go, African countries. Actually, the colouring on that map is decided by another plugin for QGIS that I wrote, which looks at the adjacencies of all the countries and doesn't colour any two adjacent countries the same colour. Does that exist in ArcGIS? Is anyone there? Okay, well, it chooses a nice range of colours, and it tries to minimise the colours. I think it probably finds 5 or 6 colours. And it looks at the adjacencies, so you don't get two of the same colour together. It's a neat little plugin I wrote for QGIS. Took me a day. Makes pretty base maps. So there's your pretty base map. Now the user has just been driving around and has just got a new survey. So they've gone to some location in the yellow column, X and Y, and they've tested the number of people in the blue column, and the number of people who said, yes, I've seen this worm in my eye, is in the green column. So they've been driving around and they've collected this data in their spreadsheet. That's Microsoft Excel. It's the only non-open source software I'll show today. It will also work with Open Office data as well. I can read that in. So you can play with that as much as you like on your spreadsheet. But the QuantumJS plugin system lets me add extra menus along the top. So you can just do import and convert an Excel survey from a simple menu